If you are into marketing mix modeling in whatever capacity, either as a practitioner or as a brand manager or CMO, you must have heard of the concept of feature selection or variable selection. So, as the name suggests, there you just select different variables. But there's also outlier detection, which is where you decide whether or not some data points are extreme in some sense. There are certain methods of detecting outliers. Box plots are probably the most common, the most popular, and also the simplest of methods for outlier detection. Outlier detection is extremely important for understanding how much influence these points will have. Now, influence is the key word here. And I found that only 2 or 3 data points out of a data set of 4 years, nearly 1500 days, was massively causing complete disruption of the model. And so the influence in this case was of the output variables, not of the input variables. So the input variables, which in this case was mostly spends and a few other variables related to seasonality and promotions, none of those were especially different on those few days. But the target variable, the sales, was abnormally high. So clearly those few days were having a disproportionately large impact on the outcome on the model itself. So the accuracy was getting distorted, and there can be different ways of dealing with that. But the first step here is to actually identify some data points, some observations, some days in this case, because it's time series data always that we are talking about whenever we are doing and not cross-sectional. For those few days, we had to identify the fact that they were abnormally high. There happened to be Easter days in the case that I was handling. It was a data set that was from 2022 to 2025, 4 years of data, but it was only in 2024 that Easter days, few days of Easter, the sales numbers were abnormally high. It absolutely made no sense because the spend levels were normal and there was also no known other variable. There had to be actually a case of omitted variable. But to arrive at this conclusion, I first had to identify that. And of course, a simple, naive, even visual observation of graphs can also give you that. In this case, it was very easy. But sometimes understanding influence can be pretty difficult, and sometimes models can be extremely impacted by a few data points, either because of the spend or the input variables, any other input variables, or even sometimes because of the target variables. It can affect the model differently. And to understand this influence, we can construct something called an influence plot, which is based on the concept of Cook's distance and its two components. Now, the Cook's D or the Cook's distance is a composite metric that tells you how influential certain data points are. You use a threshold like say 4 by D, which just tells you like if the point is far from the fitted line, and therefore you can understand the influence of the data points in question which break that threshold or are below the threshold. Of course, if it's below, it's fine. So the Cook's distance is a composite metric of two different other metrics, which is leverage and residual, specifically the one we are going to use in this example. Now you see this plot in front of you is called a studentized residual. A residual is nothing but just the difference between the predicted outcome and the observed outcome values. And then as residual is nothing but standardizing that residual by dividing it with standard deviation. The leverage is nothing but the influence of the X points of the spend variables, the input variables in this case. So it has got nothing to do with the outcome variable. So how much input variables and output variables, how these two are combining together to have an influence on the model. This is a very nice way, and I have an interactive tool that I just created to illustrate this point. If I change around the different variables, there are lots of gray points, and all of these gray points are on the fitted line, on the regression line. There are 3 other points apart from that, apart from the gray points. There's an orange point, there's a green point, and then there is a yellow point. What's happening here is that all of these are in the safe zone because they are under the thresholds of leverage and residual. So if I go here to this table below, I will look at Cook's distance here. Cook's distance is basically, like I said, how influential the point is. None of these points are exceedingly influential, which is why they satisfy the conditions of the thresholds of leverage and studentized residual, which is plus minus 2 for residual, and for leverage it is 2p by n, p being the number of parameters, n being the number of data points. P by n is actually where it will always converge, typically in regression, and therefore 2p by n is p by n on an average, so 2p by n is considered as the higher threshold. This can also be varied, but in this case it satisfies the condition of 2p by n. So all of these are in the safe zone in a sense, so none of these are really problematic points. Now if I start changing it, I bring in one of the points much higher, we'll see that the regression line has immediately shifted. So just how much influence it has on the line, the regression completely changed from, you'll see the equation has changed as well, and how much the regression line has shifted as well. So the other 2 points, points A and B, continue to remain in the safe zone. So this is something that is very interesting, and this can be very useful in deciding whether or not some points are influential. And this is something that probably should be used more often, but I think much more attention is generally given to feature selection. Much less attention is given to EDA techniques like outlier detection. I think this needs much more attention. What I have not discussed though is what to do if it lies, suppose, in the danger zone where it has high leverage as well as high residual. So first of all, you have to understand what it really means philosophically. What does it mean? Your spend levels are very high on few days in your entire data set. The spends were very high on those days, but even spend wasn't able to explain the massive difference in outcome variables. This residual, by the way, this can be on either side. Like, it can be that the spends were very high, but your revenue was very low. Unfortunately, that can also be the case, but in many cases, probably it would be that your spends were very high, but your residuals were positively very high as well, meaning that they were far higher than the median or the average in terms of the sales or revenue. That then means that the higher spends were also not able to explain it. There could be other factors, like typically if it's an offer period or a seasonal period, some seasonal element will probably be able to explain that, but you have to figure that out. That's the point. Sometimes though, despite having all measures like offer related variables and seasonality variables, like the example I just gave, because it was a one-off thing, one way of dealing with this is to use its dummy variable. You would use a dummy variable in such cases, but in this case, it wasn't Easter itself. Like, it wasn't the seasonality component of Easter that was causing it, because it wasn't present in the other years. It would have been explained otherwise. So naturally, that particular variable, for that particular dummy variable, which would be explaining only these 3 data points, would have very low explainability in the entire model as such, because this was an event or a phenomenon, whatever you call it, or a fluke or an exception. This did not have any recurrence on, or either prior to it or later. So therefore, this was a very strange case indeed, and it needs to be dealt with separately. I'm not going to go into this video and as to how you can deal with these points and deal with such situations in general. Dropping the points can be an extreme solution. If you do that, how you can deal with it, it will naturally give rise to more problems as well. Those problems are going to arise because you're typically dealing with time series data, right? You have a date column or a day column. Either it is weekly, or if you have aggregated it, or it could also be daily if you're using a daily data set. The point is that it's difficult to just drop it and forget about it, because it's going to give rise to more issues. For instance, if you're using, say, a geometric add stock or some sort of add stock or carryover effect, then it's most likely going to use some sort of recursive function, recursive form, right? It's going to depend on past values. If you delete some values in the historical timeline, it's going to probably mess up the entire calculation. Yeah, lots of things to discuss. I'm not going to discuss that in the video. Hopefully in a future video, I'll discuss the ways to deal with that. If you're in a hurry to know the solution to that, you can also get in touch with me. You can comment below to express interest, or you can get in touch with me over LinkedIn. By the way, I do keep sharing such videos from time to time, so do give my channel a follow if you want to see such content and don't want to miss out on such cool stuff. But so much for this video. I hope you have enjoyed it. Any questions, please let me know in the comments. Always happy to have good conversations, and I'll see you in the next one. Thank you.